Hello. In continuation with our last lecture of qualitative analysis, where we had stopped at the detection of anions in a particular mixture and the ions which were detected in the mixture, the interfering ions like phosphate, borate, fluoride and oxalate, they interfere in the cation analysis from group 3 onwards. This is because the medium till group 2 is acidic, and as soon as the medium changes to alkaline in group 3, these anions precipitate out and thus interfere in the cation analysis. So, before the start of group 3 cation analysis, these particular 4 ions have to be removed, and then the analysis of the cations needs to be proceeded on with. Testing for anions in presence of each other, where we have sulfide, sulfite, sulfate and thiosulfate in presence of each other. These ions have similar tests, hence need to be identified in presence of each other, since they interfere and give similar results in certain tests. So, in this test, 1 ml of the soda extract is taken in a semi-micro test tube and a pinch of cadmium carbonate is added. The test tube is shaken and then centrifuged. Cadmium carbonate is not to be added if the indicatory test of sulfide ions is not observed, because cadmium carbonate needs to be added for the detection of sulfide ions only. So, if sulfide ions have not been indicated in the test earlier, then cadmium carbonate needs not to be added, because there is no need of adding additional solutions in the mixture. Upon adding cadmium carbonate, if there is appearance of a yellow color residue, then it is due to the sulfide ions. So, as the equation goes, the sulfide ions react with cadmium carbonate to give yellow colored cadmium sulfide precipitates. So, this confirms the presence of sulfide ions in a mixture of the 4 ions which we have just seen: sulfide, sulfite, sulfate and thiosulfate. This centrifugate, after the residue is separated, the centrifugate is taken and to the centrifugate 1 ml of barium chloride solution is added. The solution is then again shaken and centrifuged. Now, at this stage we have separated cadmium sulfide from the whole mixture. If upon addition of barium chloride a residue is obtained, then that residue will be white in color and will be tested for the presence of sulfite and sulfate ions, whereas in the centrifugate we will test for thiosulfate ions. So, coming to the test for thiosulfate ions first, the centrifugate is taken in a semi-micro test tube and is acidified with dilute acetic acid. The acidification of this centrifugate is to be done with acetic acid only and not any mineral acid, because thiosulfate tends to get decomposed in presence of any mineral acid. So, acetic acid is a weak acid which will not decompose the thiosulfate ions. This is then warmed to remove carbon dioxide, and then 2 drops of silver nitrate is added to this solution. Upon the addition of silver nitrate, if white precipitates turning yellow and then finally black are observed, this confirms the presence of thiosulfate ions in the mixture. Coming to the residue part, in which we need to test for sulfite and sulfate ions, the test which needs to be performed is the residue is washed and dilute HCl is added to it. This is then centrifuged. If some residue is left undissolved, in this case even on heating, then in the residue sulfate ions are tested, and in the centrifugate sulfite ions are tested, because sulfate ions remain insoluble in the presence of dilute HCl, whereas sulfite ions tend to get dissolved in dilute HCl upon heating. Testing for sulfate ions in the residue, as you can see in the diagram, the white color of the precipitate or the residue which is obtained, where 5 drops of concentrated HCl are added to this residue. If the residue still does not dissolve, then the sulfate ions are present. If the residue dissolves, then sulfate ions are absent. Testing for sulfite ions in the centrifugate. If on addition of dilute HCl, the residue gets dissolved, the one which we had discussed in this previous slide, if the residue gets dissolved, then to this solution 5 drops of chlorine water are added along with 3 drops of barium chloride solution. The semi-micro test tube is then heated and is then scratched on the walls with the help of a glass rod. Appearance of a white precipitate which is insoluble in concentrated HCl confirms sulfite ions in the mixture. Now the reason for this is, how does this happen is that the chlorine water, it oxidizes sulfite ions to sulfate ions, and hence it precipitates out as barium sulfate on the addition of barium chloride, which remains insoluble in concentrated HCl. That means we have first converted sulfite to sulfate and then performed the same test as for sulfate, but the test which is observed is confirming the presence of sulfite ions in the mixture. Coming to the next set of anions which need to be tested in presence of each other, since they are again giving similar kind of tests, since they have similar properties, and these are chloride, bromide and iodide. Since all the three are halides, they have almost similar properties, so they tend to interfere in the test for each other. So to detect them in presence of each other, a stepwise procedure needs to be followed. Step 1 is considered for the iodide ions. In this case, 1 ml of the soda extract is acidified with dilute sulfuric acid, and then 1 gram of sodium nitrite solid is added to the test tube. This test tube or the semi-micro test tube, as we are performing the experiment in, is heated. If there is appearance of violet vapors, this indicates the presence of iodide ions in the mixture, because these violet vapors are of iodine. And what has happened is that the sodium nitrite which has been added to the soda extract along with dilute H2SO4 has oxidized iodide first to iodine, which is producing violet vapors, since iodine is highly volatile. In this case, iodide is the first one to get oxidized to iodine, as according to our chemistry knowledge, which says that iodide has the largest size and the ions which have large sizes tend to get oxidized easily, that means tend to lose electrons easily. So iodide gets oxidized first to iodine and there is an appearance of violet vapors. This can further be confirmed by placing starch paper or a filter paper or a normal paper which is dipped in starch solution on the mouth of the semi-micro test tube. This paper will turn blue, since iodine will react with starch to produce a starch iodine complex which is blue in color and will confirm the presence of iodide ions. If there are no violet vapors, instead only brown vapors are seen upon the addition of sodium nitrite, then iodide ions are absent. Moving on to the second test, which is for the bromide ions, as the next ions which are to be identified are bromide ions. This solution above is again heated by adding more of sodium nitrite crystals and more of dilute sulfuric acid to remove iodide ions completely. This is indicated by the formation of only brown vapors of NO2. The violet vapors of iodide will cease to come, and then only brown vapors of NO2 will be observed, which indicate that iodide has been completely decomposed to iodine and has been removed from the solution. After that, a clear solution is obtained. This solution is then cooled and the layer test for bromide ions is performed in it. The layer test, which we have discussed earlier in the anion analysis scheme. If there is a brown orange color in the organic layer, it confirms the presence of bromide ions in the mixture along with iodide ions, or as we say, in the presence of iodide ions. The third test which needs to be performed in continuation is the test for chloride ions in the mixture. After testing for bromide, the aqueous layer is then taken, that is after the separation of the organic layer in which the layer test for bromide had been performed, and the dilute nitric acid is added to it. After that, silver nitrate solution is added, and the appearance of curdy white precipitates at this stage confirms the presence of chloride ions in the mixture. So, we have discussed the presence of iodide, after that bromide, and further chloride ions in presence of each other in a particular sequence, wherein iodide ions are detected first and then bromide and further chloride. The chemistry involved in these particular reactions and in these particular tests has already been discussed in anion analysis scheme. Coming to the next set of ions in presence of each other is the nitrate and nitrite ions in presence of each other. Again, nitrite and nitrate have the similar tests, they have almost the similar chemistry, so they tend to interfere with each other, and hence they have to be detected in presence of each other also. So, to 1 ml of the soda extract, dilute sulfuric is added to acidify it. Then a few crystals of urea are added and the solution is heated. After destroying the NO2, that is upon heating the solution, NO2 is produced, and after removing all the NO2 on completion of heating, nitrate ion is tested by the brown ring test or the aluminium powder test. And as the chemistry goes over here, so nitrite ions which are present as for example in the terms of sodium nitrite are reacting with urea and HCl to produce sodium chloride, water, carbon dioxide and nitrogen. This reaction is the example of decomposition of nitrite ions, wherein the nitrite ions have been removed and the remaining solution is tested only for nitrate ions. So, this is a test for the detection of nitrate in the presence of nitrite, where nitrite has been first removed and then nitrate is detected. Coming to the next set, that is nitrate ions in presence of bromide and iodide ions. Now, how do nitrate ions interfere in the presence of bromide and iodide ions? That is, bromide and iodide both produce colored fumes along with concentrated sulfuric acid, and nitrate also produces brown colored fumes in the concentrated sulfuric acid test. So, nitrate tends to interfere in the test of bromide and iodide. So, for this 1 ml of the soda extract is acidified with dilute sulfuric acid. After that, a few crystals of potassium iodide, few drops of starch solution and a pinch of zinc dust is added and the test tube is shaken well. A blue color indicates the presence of nitrate ions. This test is also performed or given by nitrite ions. So, first nitrite ions need to be removed and then only nitrate ions need to be confirmed in the presence of bromide and iodide. This particular test will not be given by bromide and iodide ions. Coming to the next set of ions in presence of each other, that is oxalate and fluoride, again in presence of each other as they interfere with each other's tests. So, 1 ml of the soda extract again is taken and acetic acid is added to it to neutralize it, since the soda extract is an alkaline solution. After that, calcium chloride solution is added. Upon adding calcium chloride solution, a white precipitate which is obtained indicates the presence of oxalate or fluoride or both oxalate and fluoride ions. So, how to distinguish between whether the precipitates are of oxalate or they are of fluoride? The solution is this then centrifuged and the residue is taken and to the residue dilute sulfuric acid is added. The precipitates will dissolve in it. In this case, if the precipitates dissolve, then this solution is taken, it is warmed and 2 drops of dilute KMnO4 solution are added to it. If the dilute KMnO4 solution decolorizes, then it confirms oxalate ions in the mixture. If upon adding dilute KMnO4, the decolorization of KMnO4 does not take place, then that means the white precipitates were due to fluoride ions and not due to oxalate ions. And this is because of the fact that KMnO4 is an oxidizing agent which oxidizes oxalate ions to carbon dioxide and water, and itself KMnO4 gets reduced to manganese in the +2 state, which is a colorless state of manganese. So, this is the explanation again which can be seen that the reduction of Mn7 plus, that is manganese 7 plus in KMnO4 takes place to Mn2 plus by oxalate ions, which itself gets oxidized to carbon dioxide and water. This does not happen in the case of fluoride ions, and this is how the color change takes place, that is a pinkish brownish color of KMnO4 changes to a colorless solution upon the presence of or reaction with oxalate ions. Coming to the detection of carbonate and sulfite ions in presence of each other, both carbonate and sulfite ions give a slight effervescence with dilute sulfuric acid and they can be detected in the dilute sulfuric acid group. So, to 0.5 gram of the mixture, this test can be performed directly with the mixture. An equal amount of solid potassium dichromate is added to it. The solution turns orange because the color of potassium dichromate is orange. Hence, upon the addition of solid potassium dichromate, the solution will turn orange. Then, dilute sulfuric acid is added to it and the semi-micro test tube is heated. As you can see in the diagram and the figure, there is an orange color of potassium dichromate and ultimately it changes to a green color, which is further discussed. If upon heating, there is an evolution of a colorless gas with a brisk effervescence and the gas turns lime water milky, then this confirms the presence of carbonate ions in the mixture, and the solution in the semi-micro test tube, which was being heated, now turns green from orange, then this confirms the presence of sulfite ions also in the mixture along with carbonate ions. So, as the chemistry goes over here, the carbonate ions are reacting with sulfuric acid to produce carbon dioxide, which on reaction with lime water, that is calcium hydroxide, produce calcium carbonate, which is providing milkiness in the solution. Sulfite ions on reaction with sulfuric acid produce sulfur dioxide gas. Sulfur dioxide is a reducing gas which reduces chromium in the +6 state in potassium dichromate, which is orange in color, to chromium in the +3 state, which is green in color. And this is how the color of the solution changes from orange to green, which then confirms that sulfite ions are there in the mixture along with carbonate, and these sulfite ions have produced sulfur dioxide, which has caused the solution to change from orange to green in color. Now, once the ions have been detected in presence of each other and the individual anions have also been detected according to the scheme which has been discussed earlier, we come to the systematic analysis of the cations in the mixture. Since a salt is composed of both cation as well as anion, so after the anion analysis, we then proceed on to the cation analysis. So, once anions have been detected in the mixture by the systematic analysis, the cations need to be detected by again a systematic analysis. For this, a separate scheme needs to be followed. Anions need to be detected first and then cations, because if there are any interfering anions, they can be detected and removed before proceeding for cation analysis. As we have discussed that interfering anions will interfere in the cation analysis before group 3. Ammonium cation is detected at the start of the analysis, even before the analysis of the anions along with acetate ions. And this is because ammonium cation is detected by its smell test, and smell tests need to be performed at the very start of the mixture analysis. And the test for ammonium cation has already been discussed earlier. For the sake of convenience, cations have been divided into 6 groups, where the cations in a same group have the same precipitating agent. For the detection of cations, a mixture solution needs to be prepared first. So, whenever anions or cations need to be detected within a particular mixture, its solution has to be first made, because anions can be detected only in solutions when they dissociate into their respective ions, when the mixture dissociates into its respective ions. This solution of the mixture is termed as the original solution or the OS. The method of preparation of OS: 1 gram of the mixture is taken in a semi-micro test tube and dilute HCl is added to it. If the mixture is soluble in dilute HCl, then cations belonging to group 1 are absent, or as we say, group 1 is absent in the mixture. If the mixture is insoluble in dilute HCl, then it is dissolved in concentrated HCl by adding concentrated HCl and boiling it. And if any residue is obtained even after boiling the mixture with concentrated HCl, then it is analyzed separately under the scheme of insolubles.